Module 2, Lecture A, Lists and Tuples. By the end of this lecture, you will be able to create lists and tuples to represent ordered engineering datasets, use indexing, slicing, and iteration to access and process sequence values, and compute summary results from sequences using loops and built-in functions. Ordered engineering data. List basics. Lists are useful in engineering because they store data in the order that gives it meaning. Ordered values, such as temperature, voltage, pressure, or bridge deflection measurements, help reveal patterns and changes over time or space. By preserving sequence, lists make it easier to interpret how a system is behaving. Lists are useful in engineering because they can grow and change as data becomes available. They can store different kinds of information, such as measurements or labels, which makes them helpful for both raw data and descriptions. Because lists can be updated, they are well suited for correcting, adding, or reorganizing information during analysis. When designing lists for engineering data, each position should have a clear and consistent meaning. Values might represent fixed intervals, physical locations, or trial results, but the mapping must stay reliable. This structure prevents confusion during analysis and supports accurate computation in real-world workflows. Python code, list basics. Lists store ordered engineering data, where each position keeps the meaning of the measurement sequence. Built-in tools can then quickly summarize the stored values. We create an ordered list of pressure readings in kilopascals. Keeping the values in measurement order preserves their sequence, making the data easier to access and work with later. A sensor names list stores 3 labels: inlet, midpipe, and outlet. Keeping these labels in order makes it easy to refer to each sensor by its position and helps maintain consistency when working with sensor data. Indexing lets you access specific items in a list. The first element is found at index 0, while the last element can be retrieved with -1. This makes it easy to get the beginning and end of a dataset without knowing the list's length. Slicing is used to extract part of the pressure readings list. In this case, it selects the 2nd through 4th elements by starting at index 1 and stopping before index 4. This helps focus on a specific segment of the data for closer analysis. A new pressure reading is added to the end of the existing pressure list using the append method. This keeps the data current, while preserving the order in which measurements were collected. Average pressure is found by adding all the pressure readings and dividing by the number of readings, giving one central value for the data. The pressure range is found by comparing the largest and smallest readings, showing how much the measurements vary. The output summarizes pressure sensor data by showing the recorded readings, the sensor labels, and key positions in the list, including the first, last, and middle values. It then reports the average pressure and the pressure range, both rounded to 2 decimal places, to give a quick view of the typical level and overall variability. This script shows basic Python list work using pressure readings and sensor labels. It retrieves selected readings, slices the middle values, adds a new reading, and then calculates the average pressure and overall range. Finally, it prints the updated readings, sensor order, selected values, and rounded summary statistics, giving a quick example of list manipulation and simple analysis. Tuple data. Tuples are useful for storing ordered groups of values when each position has a fixed meaning. In engineering, they can represent compact records such as coordinates or material measurements, where individual values matter, but the sequence defines the complete data unit. This makes tuples a clear way to keep related measurements organized and consistently interpreted. Tuples are immutable, so their contents cannot change after they are created. This makes them useful for fixed data that should stay consistent, such as component dimensions, calibration constants, or a sensor location. Lists are better for values that need to change, while tuples help protect the integrity of complete, stable records. Tuples help engineers organize related data in a compact, predictable order. They can represent robot waypoints, structural nodes, or environmental readings by grouping fixed pieces of information such as positions, identifiers, times, and measurements. This makes tuples a deliberate choice for clear and consistent ordered records. Python code, tuple data. Tuples are used to store ordered engineering records, where each position has a specific meaning. Their contents are fixed, so values cannot be changed in place. Tuples are used to group related values in a fixed order that cannot be changed. Examples include storing coordinates, a sensor reading with its ID, date, and temperature, or material properties such as density, tensile strength, and thermal conductivity. Because each value stays in the same position, tuples help keep data consistent and easy to interpret. A tuple stores values in a fixed order so you can access each item by its position. In this case, the first value gives the x-coordinate, the second gives the y-coordinate, and the third gives the elevation. This works reliably because each position in the tuple has a consistent meaning. The sensor record is unpacked into 3 separate values: the sensor identifier, the date, and the temperature. This makes each part of the record easier to use individually. Then the length function is used to count how many fields the record contains, which can help with validation or iteration. Calculate the total of the coordinate values, then divide by the number of coordinates to get their average. Separately, use the maximum value function to find the largest material property, which represents the strongest value in that set. The print statements give a quick overview of engineering data stored in tuples. They show the full coordinate tuple, its individual position-based values, and the unpacked sensor record, including sensor ID, date, and temperature. They also report the number of fields, the rounded average of the coordinate values, and the largest value from the material properties tuple. This script shows how Python tuples can store fixed, ordered engineering data, such as coordinates, sensor readings, and material properties. It demonstrates accessing values by position, unpacking a record into separate variables, and using built-in operations to find lengths, averages, and maximum values. Overall, it highlights tuples as a compact, immutable way to organize and process small sets of related data. Named data sequences. Named data sequences keep ordered data clear by giving meaning to each position. This is useful in engineering, where measurements or settings may otherwise be hard to interpret from position alone. Naming the positions improves understanding, reduces confusion, and supports more accurate analysis and team communication. In engineering, named data sequences make ordered data easier to understand and less error-prone. Instead of relying on users to remember which position holds values like sample identity, load, displacement, or temperature, each element is clearly labeled. This improves communication and safety across engineering fields where accurate interpretation of data is essential. Named data sequences make engineering data easier for both computers and people to use. Unlike plain lists or tuples, they attach meaning to each data point, reducing reliance on memory and improving clarity. This becomes especially important as datasets grow, workflows become automated, and teams need to collaborate reliably. Python code, named data sequences. Named sequences give ordered engineering records clear labels while keeping each value in its original position. This improves readability, and the example uses Python's built-in named tuple records. Importing the named tuple function from the collections module lets us create simple data-holding classes with named fields. This makes structured data easier to read and use because values can be accessed by name instead of by position. It is especially helpful when clarity matters in engineering and data science code. A named tuple called sensor reading is created using the named tuple function from the collections module. It defines labeled fields for temperature, pressure, flow rate, and timestamp, making sensor data easier to read and access by name. This improves clarity, especially in engineering work, where meaningful field names help prevent confusion. A new sensor reading named tuple instance is created to represent one engineering data record. It stores values for temperature, pressure, flow rate, and timestamp, allowing each value to be accessed by name for clearer, easier data handling. A named tuple can still be accessed by position, just like a regular tuple. Here, the first item is retrieved by its index, giving the temperature value even though the field also has a name. Accessing a value by its field name makes the code easier to understand. Instead of using a position in the data sequence, you retrieve the temperature directly from the reading object by name, which clearly shows what data is being used. A list is used to store several structured sensor readings. Each reading is a named record containing temperature, pressure, flow rate, and timestamp values, with 3 samples taken between 9 o'clock and 10 minutes past 9. This structure makes it easy to organize and access each sensor measurement consistently. First, confirm that the readings list contains exactly 3 records. Then check that each record has 4 values, matching the fields in the sensor reading name tuple. These checks ensure the data structure is consistent and ready for further processing. To find the average flow rate, take the flow rate value from each reading, add those values together, and divide by the number of readings. Using named fields makes the calculation clear because it shows that the average is based specifically on flow rates. This example shows how to inspect and use a sensor reading stored as a named tuple. It first prints the full record, then retrieves the temperature by both index position and field name, with the field name being easier to read. It also calculates the average flow rate across all readings, rounds it to 2 decimal places, and prints the field names to show the data structure. This script shows how named tuples can make sensor data easier to read and manage. It creates a structured record for values such as temperature, pressure, flow rate, and time, allowing each value to be accessed by position or by a descriptive name. It also stores multiple readings, checks their structure, and calculates the average flow rate. Overall, the example shows how named fields improve clarity and maintainability compared with relying only on indexes. Access patterns. Indexing basics. Indexing lets you access a specific item in an ordered sequence, such as a list or tuple, by using its position. Most programming languages start indexing at 0, so the first item is at index 0, and the second is at index 1. Thinking of an index as an offset from the start helps explain this convention. Indexing is useful for selecting a particular value from a sequence without changing the rest of the data. Indexing lets you locate a specific item in ordered data, such as the first sensor reading for a baseline or the last reading after a test. This is useful whenever position matters, including data like robotic arm coordinates or pipeline pressure measurements. By using indexes, the structure of the data stays connected to the process or model that produced it. Negative indexing lets you access items from the end of a sequence, such as getting the most recent result without counting every element. It is useful when the last entry matters, while earlier entries show past progress. However, using an index outside the sequence can cause errors, so it is important to know the data order, valid range, and which position matches your question. Python code indexing basics. Lists store ordered engineering measurements, and indexes let you retrieve a specific value from the sequence. Negative indexes count backward from the end of the list. We store 5 temperature readings in chronological order so they can be treated as a sequence of measurements over time. This organization makes it easy to access, compare, and use individual readings in later calculations. A tuple is used to store fixed time labels for the temperature readings. It contains 5-minute intervals from 0 to 20 minutes, increasing by 5 each time. Because tuples cannot be changed, they are appropriate for representing these constant measurement times. The code first checks that the temperature readings and time labels have the same length, so each reading matches one time point. If they do not match, it raises a value error to signal inconsistent data. This protects data integrity and prevents problems when the paired values are used later. Use the first item in the temperature list to get the baseline temperature, and use the matching first item in the time labels to identify when it was recorded. Together, these values provide the starting point for later comparison or analysis. Using index 2 lets us access the third item in a sequence. In this example, it retrieves the third temperature, 22.8 degrees Celsius, and the third time label, 10 minutes. This shows how positions can be used to extract specific data from lists and tuples. Negative indexing lets you quickly access the last item in a sequence without knowing its length. Here, it retrieves the most recent temperature reading from the temperature list and the matching final time label from the time tuple. To find the temperature change, subtract the starting temperature from the final temperature. The result shows how much the temperature rose or fell during the recorded period. The program summarizes a set of temperature readings by first showing the full list, then identifying key points in time. It uses the first reading as the baseline, displays the third reading to show progress, and retrieves the final reading using negative indexing. It then reports the overall temperature change from the baseline to the final value, rounded to 2 decimal places. This script shows how list indexing can be used to work with temperature readings over time. It first confirms that the temperature and time data match in length. Then it retrieves key readings, such as the first, third, and final values using positive and negative indexing. It also calculates the change from the first to the last temperature and prints the main results. Slicing sequences. Slicing lets you take a continuous section from an ordered sequence, such as a list or tuple, without using the entire sequence. It is useful when the order of the data matters, such as values arranged by time or space. Instead of selecting items one by one, slicing helps you work with the specific range of data you need. A slice uses a start and end position, but it includes values only up to the end, not the end itself. This makes slice lengths easier to control and helps adjacent slices fit together without overlap. You can leave out the start or end to select from the beginning to the end, or to remove unwanted readings near the edges. Slicing can use a step pattern to take values at regular intervals, which helps when you only need a sample from a large dataset. For example, you might review every temp sensor reading, or every few positions in a dense robot path to see the overall pattern more easily. The slice creates a new sequence of selected values, while leaving the original data unchanged. Python code, slicing sequences. Slicing lets you select meaningful sections from ordered data, such as engineering readings that arrive in sequence. The starting boundary is included, but the ending index is excluded. We store hourly temperature readings in Celsius in a list, so the data can be accessed and analyzed over time. This makes it easy to examine specific parts of the sequence, such as warm-up, stable, and shutdown periods, by working with selected segments. Temperature readings can be sliced into phases to analyze parts of a test without changing the original data. The first few readings represent warm-up, the middle readings capture the stable period, and the final readings show shutdown. This makes it easier to focus on each segment separately. Selecting every second temperature reading uses slicing with a step of 2, which skips every other item. This gives a quick sample of the data while leaving the original list unchanged. It is a simple way to review part of a larger dataset efficiently. Use the length function to count the total temperature readings and record how many data points are in the original list. Then count the readings in the stable phase slice to see how many values it contains. These counts provide the basis for later analysis, such as calculating an average. Compute the average of the stable temperature readings to summarize the stable phase. Then find the maximum value among the every second readings to identify the highest recorded temperature in that interval set. The program reviews a list of temperature readings by showing the full set, then key slices for the warm-up, stable, and shutdown phases. It also displays every second reading for a quick overview, confirms the total count is unchanged, calculates the stable phase average rounded to 2 decimal places, and reports the highest temperature from the quick review subset. This script shows how list slicing can organize temperature readings into warm-up, stable, and shutdown phases, while also selecting every second reading for a quick review. Slicing creates separate views of the needed data without changing the original list. The script then reports the slices, the total number of readings, the stable phase average rounded to 2 decimal places, and the highest value found in the quick review. Looping through sequences. Looping through a sequence means visiting each value in order, so you can inspect it, change it, or use it in a calculation. This is especially useful for ordered data like lists and tuples, where each item may matter in context. Iteration handles the whole sequence automatically, making it practical for large or changing datasets, such as sensor readings or engineering measurements. When looping through a sequence, first decide whether your task needs only each value or also its position. If you are summarizing values, the value alone may be enough. But if readings are tied to times, coordinates, or other locations, the index matters too. Choosing between value-based and position-based access helps your loop match the structure and purpose of the data. Looping turns raw data into useful insights by repeatedly checking values, counting events, adding totals, filtering results, or finding patterns. It works consistently across many fields, such as energy, manufacturing, environmental monitoring, and transportation. Combined with indexing and slicing, looping is a scalable way to analyze ordered datasets, from small collections to large streams of sensor data. Python code, looping through sequences. Loops process sequence values one after another, which is useful when engineering readings need the same operation repeated. When position matters, indexes can be used to track where each value appears. We create a list to hold 6 hourly vibration readings, each measured in millimeters per second. Storing the values in a list makes them easy to access and process in later steps. A tuple is used to store the hour labels for the vibration readings covering hours 0 through 5. Because tuples cannot be changed after creation, these labels stay consistent throughout the program. This makes it easy to match each reading with the correct hour for later analysis and reporting. The code first confirms that the vibration readings and hour labels have the same length, so each reading can be matched correctly. If they match, it sets up counters to track the total vibration and the number of readings above the threshold, preparing for the loop that will process the data. Use the enumerate function to loop through vibration readings while tracking both each reading and its position. Add each reading to the running total, and use the position to match it with the corresponding hour label. The reading is compared with the engineering threshold of 3. If it is higher, the exceedance count increases, and a message reports the hour and reading value that went over the limit. To find the average vibration, divide the total accumulated vibration by the number of readings. This gives the mean vibration value, a simple summary of the data's central tendency. The code uses built-in maximum and minimum functions to quickly find the highest and lowest vibration readings in a list. This summarizes the range of the data without needing to check each value manually. The code summarizes vibration data by printing the average, minimum, and maximum values with millimeters per second as the unit. It also reports how many readings are above the threshold. If the number of vibration readings does not match the number of hour labels, it prints an error message about the data mismatch. The script checks hourly vibration readings against a threshold of 3 millimeters per second and matches each reading with its hour label. If the data lengths match, it reports any readings above the threshold, then summarizes the average, minimum, maximum, and number of exceedances. If the readings and hour labels do not match, it reports a data error. Sequence summaries. Aggregate values. Aggregate values combine individual data points into useful summaries, such as totals or averages. In engineering, these summaries help turn raw measurements, like temperature readings or cycle times, into insights about system behavior. They make it easier to support decisions and identify potential issues. Aggregate values are computed by moving through a sequence and updating a running result for each element. This can produce summaries such as a total, a count of items meeting a condition, or the largest value. The essential pattern is to examine each element, determine how it affects the summary, and carry the updated result forward. Aggregate values are useful when they match the question and are interpreted in context. Totals, maximums, counts, and averages each summarize data in different ways, but they can hide important details such as extremes. Their reliability depends on assumptions like complete sequences and consistent units. Computing aggregates is both a programming task and an analytical skill that helps turn raw data into informed conclusions. Python code aggregate values. Aggregate values summarize sequence data in engineering. Loops can build these summaries one element at a time, while built-in tools compute common summaries more directly. Temperature readings in Celsius are stored in an ordered list, where each value represents a point in the sequence. This structure makes it easy to move through the data and perform calculations such as totals or averages to analyze temperature trends. Start by setting the running total to 0.0 so it can hold the accumulated sum of the temperature readings. As each reading is processed, its value is added to this total to build the final sum. To find the total of the temperature readings, we go through the list one reading at a time and add each value to a running total. By the end, that running total contains the sum of all readings. Begin by setting a counter to 0 to track temperature readings that are too high. Then set the safety threshold to 25 degrees Celsius, so readings above that value can be counted. The process checks each temperature reading against a safety threshold and counts the ones that are too high. This gives a simple measure of how many readings may indicate a safety concern. Built-in summary functions make it easy to analyze a list of temperatures. The sum function adds all readings. The max function finds the highest reading, and the min function finds the lowest. Together, they provide quick results without manually looping through the list. To find the average temperature, first count how many readings are in the temperature list using the length function. Then, divide the total sum of the readings by that count to get the mean temperature in Celsius. This program summarizes a list of Celsius temperature readings. It prints the readings, compares totals calculated with a loop and with Python's built-in sum function, then reports the average rounded to 2 decimal places. It also shows the lowest and highest readings and counts how many temperatures exceed the safety threshold. This script summarizes Celsius temperature readings by calculating their total, average, highest, and lowest values. It shows that adding the readings with a loop gives the same total as using a built-in function. It also counts how many readings are above the safety threshold of 25 degrees, giving a quick overview of the data's key statistics. Built-in summaries. Built-in summary functions make it easy to analyze sequences, such as sensor readings or production times, without writing loops. They quickly provide totals, counts, and extreme values, helping you understand overall system behavior instead of individual data points. This makes tasks like estimating energy demand or identifying peak vibration levels faster, clearer, and less error-prone. Built-in summaries make code clearer by showing the intended operation, such as finding a largest value, minimum value, or average. In engineering, this clarity matters because others may need to review or modify the code. Compared with writing loops, built-in summaries reduce errors and help turn raw data into useful information for decisions and safety checks. Built-in summaries are useful, but they only make sense when the data is valid for the operation. Empty sequences, missing readings, or out-of-range values may need to be checked or cleaned first. These summaries pair well with iteration and slicing, helping you focus on recent data or compare time intervals. In engineering, they often provide a starting point for finding anomalies or preparing reports. Python code, built-in summaries. Summary functions give quick descriptions of ordered engineering measurements, and built-in functions help avoid errors from writing manual loops. These summaries work with both lists and tuples. The program stores 6 hourly pump power readings as floating point numbers in a list. This makes it easy to work with the data later, such as calculating totals or averages. A tuple is used to store the fixed test load limits of 12, 15, 18, and 21 kilonewtons. Because tuple values cannot be changed, this helps keep the engineering test parameters consistent and reliable. To analyze the pump power readings, Add all the values to find the total energy consumption. Then count how many readings are in the list, which shows the number of data points and supports later calculations such as averages. To summarize the pump readings, identify the highest and lowest power values. The maximum power shows peak performance, while the minimum power shows the lowest recorded output. Together, these values help describe the pump's performance range and variability. Average pump power is found by adding all recorded power readings and dividing by the number of readings. This gives the mean power consumption over the measurement period and summarizes the pump's performance. To summarize the Tuples load limits, use the maximum function to find the highest value and the minimum function to find the lowest value. Together, these results show the range of loads quickly, without manually checking each item. The code first shows the collected pump power readings, then reports the total estimated energy use in kilowatt hours by adding those readings together. It also calculates the average power by dividing the total by the number of readings and rounding to 2 decimal places. Together, these outputs summarize both overall energy consumption and typical power usage during the period. The output reports the key pump and load summaries, the minimum and maximum pump power in kilowatts, followed by the minimum and maximum load limits in kilonewtons. Together, these values show the overall span of the pump power readings and load limit data. This Python script uses built-in functions to quickly summarize pump power readings and load limits. It calculates total estimated energy, the number of readings, average power, and the minimum and maximum pump power values. It also reports the minimum and maximum load limits. The output presents these key metrics clearly, including the average rounded to 2 decimal places, without needing manual loops. Built-in summaries. Built-in summary functions quickly turn sequences such as lists or tuples into a single useful result, like a total, minimum, or maximum. They help engineers and data analysts summarize related measurements without writing loops each time. For example, they can calculate daily energy use from hourly readings or identify the weakest material sample. Built-in summary functions make code clearer by showing the purpose of an operation directly, such as finding a total, maximum, or count. Compared with writing the same logic in loops, they are easier to read, review, and maintain. In engineering analysis, these summaries provide quick checks, such as spotting large vibration amplitudes or confirming data completeness before deeper investigation. Choose built-in summaries based on what your sequence data represents. Numeric data is suited to totals, minimums, maximums, and averages, while text data is often better summarized by counts or value checks. Watch for empty sequences or mixed data types, and use loops to filter data before applying summaries when needed. Python code. Built-in summaries. Built-in summaries help quickly describe sequence data, which is especially useful for engineering measurements. Both lists and tuples support these summary operations. We create a list to store load measurements in kilonewtons. The list keeps the readings in order, which supports later analysis or summary of the data. A tuple is used to store fixed calibration values for material strengths, measured in megapascals. Because tuples cannot be changed, these values stay constant throughout the program as reliable reference points. The code first confirms that both the load readings and strength values contain data. If they do, it adds the load readings together and divides by the number of readings to find the average load. This gives a simple summary of the overall load characteristics. The code summarizes the measurements by finding the lowest and highest strength values. It also checks that both the loads and strengths contain data before doing any calculations. If either is empty, it raises an error to avoid invalid or misleading results. The code summarizes a set of load measurements by printing three values: the number of readings, the total load in kilonewtons, and the average load. The total and average are rounded to 2 decimal places to make the output clear and consistent. We summarize the strength data by reporting three values: the total number of samples, the weakest measurement, and the strongest measurement. Together, these results give a quick view of how many strength values were recorded and the overall range of the data. A safety threshold of 250 megapascals is used to identify acceptable strength measurements. The strength values are filtered, so only samples meeting or exceeding this threshold are kept. And the final output reports how many samples qualify as safe. The script summarizes engineering load and strength data after first confirming both datasets are not empty. It calculates the total and average load, finds the minimum and maximum strength values, and reports the number of readings and samples. It also counts how many strength samples meet the 250 megapascal safety threshold, giving a quick view of performance and compliance. In this lecture, you learned to create lists and tuples to represent ordered engineering datasets, use indexing, slicing, and iteration to access and process sequence values, and compute summary results from sequences using loops and built-in functions. In the next lecture, Lecture B, we will go over dictionaries and strings.
Thank you for your attention. See you all in the next lecture.